Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Kth largest sum in a binary tree, Leetcode 2583. In this problem, we are given the root of the binary tree and a positive integer k, and we should return the kth largest label sum in the tree, not necessarily distinct. If there are fewer than k labels in a tree, return -1. The label sum in the tree is sum of values of nodes that are on the same level. Note that two nodes are on the same level if they have same distance from the root. Then in example 1, for a given binary tree, there are 4 labels and some of these labels are 5, 17, 13 and 10 and k is given as 2. So we have to return the second largest label sum and that will be 13 because this is the largest sum. This is the second largest sum. So that's why we will return label sum equal to 13. Now in terms of solution, first we should compute sum of each label in the tree. And we can either use DFS or BFS for that. But we will prefer BFS because it is more natural way to compute the sum level by level. I have already covered BFS on this channel and I'll be making a dedicated video covering level order traversal level by level in the coming days. Now for this binary tree, we have following level sums. And now our task is to find kth largest element among these sums. And in this problem, k is equal to 2. And one of the easiest way to do so is storing all of these labels in a list and then sort this list in the descending order. So we will get 17, 13, 10 and 5. And now we can return kth element from the sorted list if it exists. Otherwise, we will return -1. In this example, k is equal to 2. So we will return 13. But the time complexity of this approach will be O of n, where n is the number of nodes in the tree, because we are going through each node in the tree to calculate the level sum for each level. And then based on this, we create a list of size h, where h is the number of labels in the tree. And to sort this list, that will take h log h time. And in terms of space complexity, it will be O of h, because we are storing these h label sums in a list. And in the worst case, h can be equal to n, because the tree can be unbalanced. So in this case, the time complexity will be O of n log n, and the space complexity will be O of n. And now the question is, do we really need to sort this array explicitly? Is there a data structure more suitable for finding the largest element in an efficient way? And the answer is yes, that data structure is MaxHeap. So how about when we are actually calculating the level sum for each level, instead of storing all of these elements in a list and then explicitly sorting it, we actually store them in a MaxHeap. And once we have added all the level sums, then we will extract the maximum element from the heap k minus 1 time and discard them because they will be larger than kth largest element, and then return the maximum element from the top of the heap, which will be our kth largest element. In our problem, k is equal to 2. So we pull out k minus 1, that is one element from the max heap, that will be 17. So we discard it. And then element at the top of the heap, that is 13, will be our answer. In this case, the time complexity will be O of n because we are still calculating all the level sums and we have to go through n elements in the tree for that. And then we are inserting those h level sums in the heap one by one, not in one go, right? And because adding the element or removing the maximum element from the max heap takes log h time, where h is the number of elements in the heap, overall time complexity to insert h level sums will be h log h. And then we are removing k minus 1 maximum elements from the heap, so that again takes k log h time. And in terms of space complexity, it will be O of h because we are still storing h elements in the max heap. And in the worst case, again h can be equal to n for an unbalanced binary tree. So in that case, the time complexity will be very close to sorting based approach. But this approach allows us to build the heap along with the creation of labels instead of first creating a list and then sorting it. So this is slightly better approach, but there is even more better approach to use min heap, where we can improve both our time and space complexity. So we can actually use min heap to maintain k largest level sums instead of storing all the level sums in the min heap. So that actually reduces the space complexity to O of k. So the idea is, each time we calculate a level sum, we insert it into the min heap. So for example, initially we saw 5, we insert it to the heap. Then we saw 17, we also insert it into the heap. And now we see 13, we insert it to the heap. But now heap size is exceeded k, that is 2. So for that, we will actually remove the smallest element from the heap because now it is no longer among the k largest elements. So now top of the heap will be 13 and 17 will be the child. And then we see label sum as 10. We add it to the heap. Now 10 is the minimum element. But now heap size has exceeded k equal to 2. So we pull out the smallest element from the heap. And now again 13 is at the top of the heap. And now we are done with all the label sums. And now there are only k elements remaining in the heap. And now what is the kth largest element? And the answer is top element of the heap, as all the larger elements are below it in min heap, and top element here is 13, so we will return 13 as our answer. Now in terms of time complexity, again we are going through n elements in a tree to create the label sums, and then for each label we are inserting an element or removing the minimum element from the heap. That takes log of k times for one operation, because at any point there are k elements in the heap, but we are doing it for h labels. So because of this, the time complexity is h log k, and the overall time complexity is n plus h log k. And the space complexity was O of k because we are storing only k elements in the heap. So if we compare this approach to previous two approaches, in the worst case h can be equal to n. So the time complexity here will be O of n log k, which is still better than previous approaches where the time complexity was going to O of n log n in the worst case. So, and the space complexity is also really nice because it is O of k instead of O of n in the worst case. So we prefer this approach. And now let's jump into the code part. First, let's initialize the queue for label or a traversal, and we will be storing 3 nodes in it. And in Java, we can use linked list implementation of queue. Let's also define min heap to track k largest labels. And in Java, we can use priority queue implementation for that. And as our answer can be long, so priority queue will also store long. Now we can start the BFS, and source node will be root, and we will run the BFS till the queue is not empty. Because we are calculating the sum label by label, first we should get the length of the current label, because later on we will add the next label to the queue. So before doing that, let's get the current label size. Also, let's define current label sum. Initially it will be equal to 0. Now we will process the node at the current label. So for each node in this label, we will pull it out, add its value to the label sum, and if it has left or right children, we will add them to the queue for the next label. Now in this loop, we have done the traversal of one label. So we will offer the label sum to the heap, and in the next iteration again label sum becomes 0 and the processing of the next label starts. But we should also check if min heap size is greater than k. In that case, we should remove the smallest element from the heap because we are storing only k largest element in the min heap. And finally, we will return the top element in the heap, but only when min heap size is greater than equal to k, because if min heap size is less than k, in that case, we should return -1 because there were not enough labels. Otherwise, we will return the top element of the min heap. Now let's run this code. Let's submit this code. Cool. I hope this video was useful to you. If it was, please like, share and subscribe. The code link containing different approaches like using sorting or max or min heap is in the description below. If you have any questions or suggestions, please write them in the comment box. Thanks for watching. See you next time.